Okay, so today we're going to get rolling with the action potential. So last time we spoke, we talked about the resting membrane potential, how it gets set up, specifically about the situation with sodium and potassium as pertains to our neurons. And we took a quick look at the shape of a neuron so that we can talk specifically about what's happening in each part of the neuron as we move through the next couple lectures. So today we're going to be talking about the actual communication between cells. So we're going to be talking about how an action potential, which is our signal down an axon to our next neuron, happens, which is going to have to do with adding up a series of changes called graded potentials until we hit a threshold. We're going to talk about the ions involved. We're going to talk about the different types of channels in the membrane involved. And then we're going to talk about how this charge actually travels down the cell. So we've been talking thus far about cells in their entirety having a membrane potential. And now that we're talking about a neuron that has this distinct shape, we're going to be talking about specific locations in this cell as having their own membrane potential. Okay. So we're going to start by thinking about how we get to an action potential in the first place. So we're going to have two types of electrical signals that we think about. Our ultimate goal is to create an action potential to communicate with our next cell, either another neuron or actually a muscle cell could receive an action potential. So those are going to be our large charges that help us communicate over long distances that run down this long skinny axon to the next cell. But in order to kick off an action potential, we're first going to have to hit a threshold in the membrane potential. So we talked last time about our resting membrane potential around -70. And nothing actually happens unless we hit this tipping point of -55. Nothing happens in terms of our cells signaling to each other. So in order to build up to an action potential, we're going to end up first focusing on something called graded potentials. So our graded potentials are what we see in this first figure, figure A. So what these graded potentials are little changes in the membrane potential. So just little changes in the membrane potential. They don't travel very far along the cell, but we're going to see that they can add up. So they can add up to get us to our threshold and ultimately kick off our cell-to-cell signaling this action potential. Okay, so just a reminder from Friday, we want to think about what's going on at the resting membrane potential. So we want to think about a potassium ion. We want to think about what direction that electrochemical gradient is for our potassium ion when our cell is at the resting membrane potential. We want to think about whether when it moves, that makes the membrane potential more negative or more positive. So let's start with this first part of the question. So does anyone want to tell me which direction the electrochemical gradient is? So thinking about outward or inward for our potassium ion. Okay, yeah, perfect. So outward. So we have two options. Potassium wants to go out of the cell And when potassium leaves the cell, does that cell become more negative or more positive? Yeah, perfect. We're moving positive ions out, so it becomes more negative. Okay, so we talked about that last time. We talked about our vocab word that we're going to see later on, that this is hyperpolarization. Okay. Also want to think about our sodium traits. We're also going to be talking about sodium. Okay. So we're thinking about the setup for our cell as relates to sodium. So we remember that we have sodium channels and potassium channels. All right, so this first one, hands up, who thinks that's true? It actually is going to be true. We're going to have slow leaking because this cell is less permeable than potassium. So it's going to be leaking slowly because we don't have many channels. Also, okay, so these things are all related. And it happens to also be true that there is a strongly directed force into the cell, but it can't be released at this point because of these few channels, this low permeability causing a slow leak. So this is something that's going to change when we talk about the action potential. That's why that's important for me. I'll just tell you the answer to this one because we have not gotten to these other two types of channels, but the channels we've been talking about, right? We haven't talked about any gates at all, right? So they're going to be non-gated. So those are our leak channels. So those leak channels were the ones we were talking about in the body of the cell, the soma, that are setting up that membrane potential. And we're going to talk about two other types throughout this unit. So graded potentials are set up for the action potential. So when we think about a graded potential, what we're thinking about is a cell reacting to a stimulus. So you're thinking about a neuron, and something's going to poke it, right? Essentially, we're thinking about like other neurotransmitters, like poking our neuron, right? So graded potential is going to be initiated by a stimulus. And that stimulus is going to cause a small change in the membrane potential. So we're going to have a little local change, essentially, right where that stimulus pokes the membrane, right? So where we have that neurotransmitter come in and poke a membrane in a specific spot, that is where we're going to have our small change in the membrane potential. So we can see that here, right? So here's our stimulus coming in. And these graded potentials do affect the rest of the cell, but the effect decays, so it gets smaller as it goes out, right? So that's what these shrinking arrows are showing. So let's say if at the stimulus rate, say it changed by 10 millivolts, right? At this location, maybe it changes by 8 here, 6 here, 4 here, and so on until it fades away. That's what we mean by decaying. So that spread is happening by something called electrotonic conduction. That just really means that these charges are spreading around. Okay? So this decremental quality means that we're fading as we move away from that spot, but we do have some changes to the membrane potential happening in other parts of the cell. What we are ultimately going to be focusing on when we think about the action potential is we're ultimately going to be thinking about changes to the membrane potential of the axon hillock, which is the sort of part that leads us into the axon, into that long skinny part. So we're going to be thinking about stimuli coming into the body of the cell, to the soma, at all sorts of places. And we're going to be thinking about what parts of those charges essentially add up at the axon hillock. We're not going to be doing like real math here. but I'm going to be using some example numbers just because I always find that helpful to sort of double check myself. So you may find that helpful as well. All right. So our purpose of these graded potentials is to determine whether we're going to kick off an action potential, which is our big, long sort of wave of membrane changes down the axon. So the threshold is the level of depolarization necessary to elicit an action potential, aka this is the number we need to get to in order to have the action potential happen. That's all that is, right? So we have to reach the threshold. When we talk about graded potentials, we'll often also talk not just about like how strong they are, not just their magnitude, but also which direction they're moving the action potential. All right. So when we say that something is excitatory, right? Something is excitatory, gets excited, the cell's getting excited. This means we're making it more likely that an action potential is going to happen. So that means we need to get closer to the threshold, right? So imagine our threshold is here. So getting closer to that threshold means we're going up, right? So our excitatory charges move us up towards our threshold of -55 from our resting membrane potential of -70. So excitatory potentials are going to depolarize the cell. Depolarization was one of those other vocab terms we got to right at the end of Friday. So when we depolarize, we're making the cell less negative, we're going up. So these two things should be linked in your mind. Exciting the cell, we're depolarizing it, we're getting it closer to this threshold. So the opposite one, inhibitory potentials, are just potentials that are making it less likely that we're going to send off an action potential. So those are just the opposite, right? So inhibitory potentials move us farther away from our threshold, which means our cell is ending up with a more negative membrane potential. We are hyperpolarizing. So hyper, we're making it more polarized. We're creating an even sort of greater negative charge on this membrane. So we're going to see these terms come back at the end after we talk about the action potential, when we start to talk about synapses and neurotransmitters and how they affect the next cell in the sequence. So we just had these tiny little bumps, not getting us up to the threshold. These graded potentials would be pretty useless. They would do nothing. So we're able to add them together. Right? So your cell is not going to react necessarily when you get just one signal, but it's going to be adding together multiple signals, multiple stimuli, coming either from multiple different parts of the cell, so coming into two different locations, say to the right and the left at the same time, or they're also going to add up if you have something poking your cell over and over and over again, right? So if you have a repetitive stimulus that happens close enough in time that the previous change to the membrane potential hasn't faded away yet, that is also going to add together these graded potentials so that we can potentially get up to our threshold. Okay. So our temporal summation, temporal just means time here. Temporal summation, so time adding them together. So we're adding them together over time. So we're going to have one stimulus. We're going to have it happen multiple times in a row, right? So you can think about it like you're thinking about two neurons signaling to each other. Say neuron number one keeps sending an action potential down to neuron number two, keeps doing it over and over again, like pulsing. You would be able to add those together using temporal summation to figure out what's going to happen to the second cell. Our spatial summation, you're going to think about a different setup of neurons, right? So here we're thinking about a second neuron in line, but maybe two different neurons are signaling to it, right? So let's say we're thinking about our neuron over here, right? And it has two different neurons telling it what to do, right? So here's another neuron. and here's another neuron. Okay. So in this case, we're going to want to be able to add together the signal we're getting from over here and the signal we're getting over from here. Okay. So in spatial summation, we're going to have different stimuli, aka here we're looking at stimuli coming from two different neurons talking to the neuron that we're focusing on, right? So in this case, we're focusing on this neuron. So two different stimuli, so coming in from two different places that overlap in time. So these first two neurons are signaling at the same time, telling the cell to do something. Okay. So in temporal summation, I'm going to draw us a couple little cells. Okay. So we're going to just look at little round cells first, although that's not what our neurons look like. So this T1, T2, T3, think about them as like different time points, right? So like 1 second, 2 seconds, 3 seconds, something like that. Right. So what we're thinking is say at T1, we're starting out everywhere at -70, right, at a resting membrane potential. We're going to think about a graded potential coming in here, our stimulus, let's say, changes this membrane potential by 10. So let's say here, we're going to get to -60 at this part of the membrane. But these charges are decremental. So maybe over here it's at -65, not as big as the change, right? Here we're at -67 and so on. And the same thing would be happening in this direction. Okay. So at time point 2, remove that stimulus, and these charges are going to fade a little bit. So now where we had -60, let's say we're getting slightly back towards our resting membrane potential. So now we're at -65. Let's say this one over here is now -67. I'll make this -70 over here. Let's say this end totally faded, right? So in temporal summation, we're then going to have that same signal come in right at the same place, right? So we're going to zap it again. So now, when we have that change of 10 millivolts, we are now at -55, right? Because we already had a slight membrane change from that first signal, and so on and so forth. We could see it decaying and getting smaller as we go around the cell, right? So that's what we're talking about when we talk about temporal summation, that we have that same signal, zap it, starts to fade away, then it zaps it again. And so that little bit that was still there adds together with our new signal. In spatial summation, right, we're just adding together two different signals, right? So we can have two different signals coming in. Okay, so we're going to come in over here. We're going to come in over here. So let's say we started at -70. Let's say these both also change it by 10. So -60, -60. Here, let's say we're at -61, -61. Right direction. And -62, -62. But in this middle here, as they start to overlap, they're going to add together. I've confused myself with these numbers, but we're going to add them together right there at the center. So the change is going to be slightly more when these charges bump into each other is the basic gist. Okay. So, yeah. Yeah, that's what I just messed up with the numbers. Probably better to think about them the opposite way, actually. So like, instead of thinking about the total membrane charge, let's say this is changing it by +10, by +10. I'm going to add now, sorry. This is +8. This is, oops. This is +8. Okay, so let's say in the center here, we're down to +6 and +6. So at this little patch, we're actually at +12. Okay. That's how we would add those together. So our total charge here would be -70 + 12, -60, -58. So that's what we're talking about when we're talking about spatial summation. Like I said, I'm not going to ask you to do any math on those. So those are just for illustration. So if that makes you more confused rather than less, just ignore the numbers. Okay. So when we think about these membrane potential changes, we use various different words to describe them, to describe the direction of that change. Okay. So our resting membrane potential, -70, is our reference point. So our depolarization is going up. All right, so depolarization, and we talked about that as being excitatory, right? So we'll sometimes refer to it that way when we're referring to signaling to the next cell. This brings us closer to our equilibrium potential for sodium, right? So we said that was like +60. Okay. Hyperpolarization is going to happen the other way. So hyperpolarization, taking us down further towards our potassium equilibrium potential of -94. Right? So those two we talked about. When we talk about the action potential, we're going to add on one more word. So our final term here, this repolarization, is just kind of layering time on here. So what we're saying is that we're going down, but we're doing it after a depolarization. So we're saying like we're going back to the resting potential. So that's what our repolarization is. So the hyperpolarization down from the resting potential, depolarization up from the resting potential, repolarization back to the resting potential after a change. And we're going to see these happening in a very characteristic order when we talk about our action potential. Okay. So this is just a reminder slide, sort of a, you want to make flashcards or something. These are types of ion channels that we're talking about for this unit. So our leak channels are pretty much everywhere. These are the ones we've talked about so far. They're just always open, and they're helping us to maintain that resting membrane potential along with our sodium potassium pump. That's not a channel, so it's not on the list. Okay. So those are setting up that resting membrane potential of -70. Now, when we're thinking about stimuli coming into the cells, those stimuli creating those graded potentials are usually going to be ligand-gated channels, right? So we're going to see them in the places where we receive signals, which are our dendrites, so the little hairs on a neuron, and on the cell body, the soma. The way they work, essentially, to draw a picture to show you. So we have our cell. We have our channel that starts out closed, right? So we're going to have a channel that starts out closed like that. Close it. A ligand is just something that binds onto something else. So when we think about neurons, we're often thinking about neurotransmitters. So we're going to say a ligand binds on, probably a neurotransmitter because we're talking about neurons. And when it binds on, what it does is it opens up that channel. So when we see it bound, I'll just draw another one next to it. When we see it bound, the bound state is going to be open. So it's changing the shape and opening that channel. All right. So we're moving from that state to that state as we bind that ligand off. So this is the like actual physiological way that we'd probably set off those graded potentials. we'd have something come bind into a ligand gated channel, and it would open either a sodium channel, depolarizing us a little bit, exciting us, getting us more towards threshold, or open a potassium channel, in which case we're going to have more potassium leak out. So we're going to get down farther towards the potassium equilibrium potential and hyperpolarize. So that's kind of the mechanism for these graded potentials. So what we're going to talk about next are our voltage gated channels. So our voltage gated channels are going to respond to voltage, aka they're going to be responding to those changes in charge on the membrane potential. So we're not waiting for something to bind onto them. They're waiting essentially until we get to that threshold. That's why we have a threshold, if they react to a certain amount of charge. So we're going to have sodium and potassium channels, voltage gated channel, and we're going to look at each of them because the sodium ones and the potassium are a little bit different. They're going to be throughout our axon where we send the signal down to the neuron. And they're also going to be in the axon hillock, which is just the first little part leading into the axon, where we're thinking about summing up our graded potentials. So they're responsible for kicking off our action potential. Then at the end, we're going to have calcium channels at the axon terminal, and their main role is going to be to release neurotransmitters. So we'll talk about them when we talk about synapses. And those will be another type of voltage gated channel, but we're not going to think about them for at least another day or two. Okay. So we're going to start with the voltage gated sodium channels. And the reason we're starting with the voltage gated sodium channels is that we know sodium is waiting. It wants to rush into that neuron, right? We're really far away from the equilibrium potential. We have a really strong electrochemical gradient because we have both our electrical and our chemical driving forces pointing into the cell. So our action potential actually is essentially a wave of sodium ions being allowed to rush into our cell. The way that happens is that we open a voltage gated sodium channel. Or really, we open several voltage gated sodium channels, kind of all in a line down the axon. Okay. So these are what the reason we pay attention to that threshold, because they open when the cell gets to negative 55 millivolts. When we reach that charge, this sodium channel opens, right? So when we start out at the resting membrane potential, we're going to see that the structure of this sodium channel is a little complex, this voltage gated sodium channel. So it actually has two gates. So it has what we call an activation gate here in the center. Right, so this is our activation gate. And this little ball on a stick is our inactivation gate. Okay. At the start, at our resting membrane potential, so when these are closed, we're going to see that the reason nothing is getting through is that that activation gate in the center is closed, but it's going to be capable of opening if we reach the threshold. The other thing that happens to be true is our inactivation gate is open, right? So we essentially have two sort of sliding doors, or you can think about like a window and a screen or something, right? They are going to both have to be open in order for sodium to get through. So when we start out, we have this activation gate closed, but the inactivation gate is open. Doesn't matter because we need both open in order to get through. Once we reach the threshold of negative 55, that activation gate opens. So this voltage gated channel gets activated. The activation gate opens. The inactivation gate is still open, right? It hasn't closed. So our sodium is going to be allowed to rush into the cell because now both our screen and our glass window are open, right? Okay, so we can get through both of these doors. After a little bit of time, the inactivation gate gets triggered and it closes over. So at this point, sodium can't get through because the inactivation gate is closed and it's not going to be able to open again until we get back to the resting state. So for a little while, the activation gate will be open, but the inactivation gate will be closed until we fully repolarize. When we repolarize, we're going to get back to our original state. This deactivation step is going to happen about a millisecond after the activation gate opens, which corresponds to roughly a charge of -30 millivolts on the membrane. So we'll trace that through as we look at the action potential. So our two gates, the activation gate is dependent on that voltage specifically. We're trying to get to -55 millivolts to that threshold. So it opens at the threshold and during depolarization, right? Because this depolarization is how we're reaching that threshold, right? So to get to the threshold, we're going to be going through a depolarization step. This is a positive feedback loop, actually. Right? We usually see negative feedback loops in physiology, but this is a positive feedback loop because if you think about it, as we open a voltage gated sodium channel, sodium comes in, right? When one sodium comes in, we depolarize a little more, right? So we go up a little more, which means that our neighboring voltage gated sodium channel can now respond to that charge and it's going to open up, right? As more and more of these gates open, our cell is getting more and more depolarized, right? Our membrane potential is going up and up, and that triggers more and more voltage gated sodium channels. Okay. So that's what's going on with our activation gate as we're allowing sodium to rush into the cell during our depolarization. Our inactivation gate is reacting to voltage, but it's also reacting to time. So it's going to let sodium flow in for about a millisecond after we reach that threshold, and then it's going to shut. So it's going to be opening during it's going to be open during depolarization to allow those sodium ions to come through. Both our activation gate and our inactivation gate have to be open. But then it's going to start to close once we hit about a millisecond, which is going to start to shut off our various voltage gated sodium channels. So that's how we're going to get sodium rushing into the cell during our action potential. We have our voltage gated sodium channels responding to reaching threshold, opening an activation gate, and then slowly closing an inactivation gate to turn themselves off after about a millisecond. The other type of voltage gated ion channel we want to think about when we think about our action potentials are voltage gated potassium channels. They're basically simpler. You maybe know a little bit less about them, possibly also. But basically what's happening with them is that when we hit 30 millivolts, this is going to be essentially at like the top of our action potential. So we'll talk about what I mean by that. But basically, when we look at that action potential, we see the same shape over and over again. Right. So we see that we go up to threshold, then we have a peak, and then we have a dip. Right. So as we're going up, right, once we hit positive 30 millivolts, this is when our potassium channels open. Okay. When we open our potassium channels, potassium wants to leave the cell. It wanted to leave the cell a little bit when we were at -70, but its equilibrium potential, right, the equilibrium potential of potassium was like -94, right? So now that we're all the way up at positive 30, we've moved much farther away from that equilibrium potential. So we really want to remove potassium at this point, right? It now really wants to move because of that change in the membrane potential, that change in the electricity. Okay, so potassium is going to rush out and it's going to repolarize back to the potassium equilibrium potential, or back towards it. It's going to overshoot the resting membrane potential a little bit, and then we're going to kind of even out. So they only have the one gate that we're interested in, right? So we don't have to think about activation gate, inactivation gate for potassium. It's just the gate on the voltage gated potassium channel. And it depends on voltage and on time, the same way our sodium channels did. Basically, we're thinking about them turning on at about positive 30, essentially. Okay. So this is going to be like kind of negative feedback on this process as well, right? So as potassium leaves, right, we're moving farther away from that positive 30, right? So this is going to kind of slow down as we get more and more negative. As we think about these, we want to be able to tell them apart. So we want to know that if we are thinking about if we mention an inactivation gate, activation gate, we're talking about our sodium channels. At rest, that activation gate. The inactivation gate, excuse me, is going to be open. The activation gate is closed. And here we see what this is going to look like layered onto our action potential. So this is a little confusing at first, so I'm going to highlight some things here. Okay. So what we're looking at here in red, this is our action potential, right? So in red, this thing, this is talking about the change in the membrane potential. So we're starting at -70. We're somewhat slowly getting up to -55, our threshold. Then we have our sodium channels opening, our voltage gated ones, rushing up to +30. So this is our depolarization. Then we go back down, repolarization. We overshoot a little, this is hyperpolarization, and then we get back to rest. Okay, so this is talking about these charges. And we're going to see that an action potential is always the same. It's always the same shape. These charges are always the same numbers. We're not going to have action potentials that are bigger or activation potentials that are smaller, because those voltage gated channels just work the way they work. They turn off and then off at those specific charges. So we're not going to add together our action potentials the way we did for graded potentials. What we can do, though, is map on the permeability of our membrane at these times, right? So when we think about the permeability of our membrane, our sodium here is in this purplish or darker blue, right? So there is very low permeability of the membrane to sodium when we start out, right? So we know that there aren't very many sodium channels in our cell at rest. So that's what's being reflected here, right? So our membrane is not very permeable to sodium. We just have a couple of leak channels, that's it. As we get to -55 though, right? So this threshold, you're depolarizing, you're opening some more and more sodium channels in order to depolarize, right? And now we're really kicking off here. So what you're seeing here is the fact that the activation gate of those voltage gated sodium channels is opening when we hit -55. So probably one sodium channel, voltage gated sodium channel senses that first, it lets in a couple charges, then its neighboring voltage gated sodium channels get to those charges, they open as well. So we're opening more and more channels, raising the permeability of the membrane to sodium by an awful lot as we depolarize, right? Then those inactivation gates start to swing closed. So as they're swinging closed, this is going to stop us from going up and up and up, right? So if we were thinking about what happens as we close those, right, like we might think in absence of anything else, right, our charge might stay kind of flat here at the top, right? Right, because just because they're closed, that means no more is coming in. Nothing coming in doesn't actually pull us down. So that's when we need to think about the potassium. Okay. So what the potassium is doing at this time, right, is initially you can see the potassium. We know there are more potassium leak channels, right? So we have a higher permeability to potassium to begin with. Not much is changing during the first part of our action potential, right? We're not having very many changes at all to those channels. But after probably about a millisecond, at the point that the action potential is reaching +30, we start to open our potassium channels. Okay. So that is what is pulling the action potential down, right? So closing these sodium channels stopped us from going up higher. right? Because sodium actually wants to get us to positive 60. That's our equilibrium potential for sodium. Right. Okay. So we didn't get all the way there because these channels closed. And now as we're opening these potassium channels, we are pulling that action potential down, repolarizing. And this is also why we have this overshoot, right? Because it takes a little while for them to close. So we overshoot a little bit. So they're also open during this hyperpolarization phase. Eventually, we even back out to our resting state. Okay. So we refer to membranes as excitable if they have the ability to generate action potentials. Membranes have resting membrane potentials, right? If we can change that resting membrane potential and kick off an action potential, we've got an excitable membrane, which is going to be true of our neurons and a little bit of our muscles. Okay. The action potential itself is this rapid, large depolarization that we use to communicate. So that's that series of voltage-gated sodium channels opening, allowing sodium to rush in, but then ultimately closing and bringing that peak back down to rest. And in our neurons, that action potential physically in space is moving down our structure of the axon, right? So here's our soma, here are our dendrites coming in, receiving signals, our axon, this part, axon hillock would be just the first part, and then our axon terminal is at the end. So here's our axon, right? So that's where we're thinking about the action potential as happening. And what I don't want you to do, so don't think about the action potential in that graph as like lying over the course of the axon. That's not what's happening. That's a time progression. So what we're going to see is happening is that we're going to have this whole time progression, this whole wave happening. First at this patch of the axon, then at that patch of the axon, then at that patch of the axon. So this is like doing the wave in like a stadium or something. That's what's happening with our axon. So when we hit the threshold membrane potential of negative 55 millivolts, our voltage gated sodium channels are opening because their activation gate is opening. Sodium rushes in, membrane potential goes up, which we refer to as depolarization. More and more sodium channels open because this is a positive feedback loop, and the cell is becoming more and more permeable to sodium because we have more and more of these channels open. Okay, so this takes us up past 0, up to positive 30. Doesn't take us all the way to positive 60 because these channels will close. Okay, so once we hit that peak, our sodium channels are closing because their inactivation gates are swinging closed. And at the same time, our potassium channels are opening, causing potassium to rush out of the cell now, pulling us back down, repolarizing our membrane potential. So this is our negative feedback loop, repolarizing, pulling us back down. Here is a sort of chart helping if you are a person who likes to study in chart format, the difference between what's happening with our voltage-gated sodium channels and our potassium-gated channels at each of the phases of our neuron. So at rest, during that peak, going up to depolarization, repolarizing down to negative 70, and then that hyperpolarization that happens after this up and down peak as we overshoot with those potassium channels before finally coming back to rest. So you can trace what's happening to the charge. So onto the membrane potential, you can trace what's happening specifically to each of the gates, where the sodium is going, what's going on with the potassium channels, and what's going on with the flow. If you want to fill out yourself a blank chart, that is a way you could study these things. So our excitable membranes are generating these action potentials. The action potential is a rapid, large depolarization for our communication. They're traveling from the cell body, starting at the axon hillock, all the way down to the axon terminal. We'll talk about what an afferent neuron means later, but basically when we start to talk about the nervous system structure as a whole, we're going to distinguish between nerves that are coming in and telling your brain things. Those are going to be your afferent neurons versus nerves that are going out and telling your body to do stuff are efferent neurons. So that's all that. Okay. So at rest, our permeability, P permeability to potassium is greater than our permeability to sodium. We know that because we know that we have more leak channels for potassium, and we know that that resting membrane potential is down towards the equilibrium potential for potassium, far from our sodium equilibrium potential. Okay. So these are all just really rephrasing things we've talked about already in a different sort of format. Okay. So we then have a series of graded potentials. So we have those stimuli coming in and zapping our cell, either one after the other, doing temporal summation, so multiple stimuli in a row in time, adding up graded potentials to bring the membrane to threshold. Or maybe we have two neurons signaling from opposite sides of the cell to one individual neuron. We can add up those things spatially, adding those graded potentials to get to the threshold. Either way, we're just trying to see if we get to -55. So we're first depolarizing to the threshold. So we're going up towards that threshold. We then have a rapid opening of those voltage gated sodium channels. This is regenerative, meaning it just like happens over and over. We slowly close those sodium channels, stopping our rise of the membrane potential. And then at the same time, our potassium channels are slowly opening, allowing a little more leak, right? So this is why we're not getting all the way to our +60, our equilibrium potential for sodium. Our sodium channels have closed at the top here. Now we're repolarizing. Our potassium channels are still open, right? So they're still open during this repolarization phase, right? So this is our depolarization. This downslope is our repolarization. And our after hyperpolarization is this phase where we're below -70. So that's our after hyperpolarization. Okay. So what we're saying is that those potassium channels have opened, holes are charged down. They stay open for a little too long, so we go below -70, but ultimately we're going to get back to our rest. Okay. Final thing is just that that sodium potassium pump is partially responsible for restoring us to -70 after our little overshoot, after that after hyperpolarization. Okay, so we'll pick up here on Wednesday.